Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone and welcome back to Physics with Beth and Beth. I'm Beth and today we are continuing our discussion of AP Physics 1 Unit 3, which is on work, energy, and power. And we're going to dive right in with a slightly more complicated example of calculating some work. So let's get started. This is our scenario here. We have a 10 kilogram box that's being pulled by a 75 Newton force at a 30-degree angle above the horizontal for 6 meters across a rough horizontal surface. Okay, that was a lot of words, but breaking this down, this is like a couple months ago when I was moving back down here to our beautiful state of Arkansas. I had a lot, and by a lot I mean a lot, of very heavy boxes of books. I hoard books a little bit like a squirrel does acorns for the winter. So we have one of these many 10 kilogram boxes of books, and it's being dragged across a rough surface, like say carpet maybe, by 75 newtons at a 30-degree angle above the horizontal, and we're moving it 6 meters. Okay, that's not too bad. Then we're also told that the coefficient of static friction is 0.40, and the coefficient of kinetic friction is 0.35. So now we're asked to find the force of friction, the work done by the force of my pull, the work done by friction, and our total work. So let's get started. Whenever you have a big old problem like this where they're throwing a bunch of different pieces of information at you, one of the easiest ways to break it down is to just draw a picture. But not just any picture, a helpful picture. So I'm going to do this over here. We have a 10 kilogram box, and it is being pulled by a 75 Newton force at a 30-degree angle above the horizontal. So my force is pulling up like this. This is the force of my pull. It has a magnitude of 75 newtons, and it is at an angle of 30 degrees above the horizontal. Okay, then we know our box has mass, and presumably we're on Earth, as that's the planet I was on when I was moving. So we have the force of gravity that's pulling straight down. But our box isn't just plummeting through to the center of the Earth, right? We know it's on a surface. There is something that is opposing gravity. And so that is going to be the normal force. Let me make this a little more straight here. And the normal force is always normal to the surface that we're on. We have a horizontal surface, so our normal force is pointing directly vertically. So this is our normal force right here. And then we're also told our surface is rough, which means friction. So we have friction at play here. Which direction is friction in? Well, it's always, as we remember from our forces unit just a couple videos ago, friction is always parallel to our surface and pointing in a direction opposite to movement, right? So we have the force of friction pointing here. There we go, and we are done. Oh, one other thing we might want to note is that our box is moving 6 meters horizontally, so I'm going to note this like this. This is delta x, and we know it is equal to 6 meters. Okay, I'm also just going to make a quick little note that our coefficient of static friction is 0.4, and our coefficient of kinetic friction is 0.35. Okay, so the first thing we're asked to do is find friction. So I'm going to erase all of this so that I have room to write. Here we go. Okay, so first step. Find friction. Well, and now this is a pretty fun one to calculate. We know that friction is equal to the coefficient of friction times our normal force. See, it's fun. Okay, please don't stop the video. Please just stick with me. I promise there will only be like a couple of terrible puns. I think that was actually my last terrible pun for today, but I make no promises. Okay, so we know that our force of friction is equal to our coefficient of friction times the normal force. Well, which coefficient should we be using? We were given two, the coefficient of static friction and of kinetic. But our box is moving, right? So when you hear moving, think kinetic. So that means we're going to be using this one right here. So I'm just going to write in a little k to note that we're using the coefficient of kinetic friction. But now we need to find the normal force. Now, this one is a little bit of a doozy because we can't just say it's equal to opposite of gravity because it's not our only force in the y direction. So actually, let's talk about all of our forces in the y direction for a moment. Well, we know that the sum of our forces in the y direction is going to be equal to the mass of our box times our acceleration in the y direction, right? So our acceleration in the y direction, our box isn't flying upwards or sinking down into the earth, it's only moving horizontally. So our acceleration in the y direction is 0. So because this is 0, we know that the sum of our forces in the y direction is likewise 0. Okay, so what are our forces in the y direction? Let's write them out. Well, pointing upward, we have our normal force. And then we also have the y component of my pull here, right? Because I'm not only pulling sideways, I'm also pulling up a little bit. So we have plus the y component of the force of my pull. And then pulling downward in the negative y direction, we also have gravity. So this is minus the force of gravity. And we know that all of those are going to sum up to 0. Okay, and now I'm going to rewrite this over here just so that I have a little more room when we're trying to find friction, the work done by the force of my pull, the work done by friction, and total work. Okay. Okay, so 0 is equal to, well, here I'm going to now just move the, well, actually, let's just start solving for some of these. Well, what is the force of our pull, the y component of the force of our pull? Well, if we do a little bit of trig, we can say, okay, well, the y component of the force of our pull, don't draw this whenever you're doing a problem on the AP exam for a free body diagram. Don't do this at home, in other words. But for our little notes as we're working this problem out, we know the y component is going to look like this, right? Where the 75 newtons of the force of our pull, that's like the hypotenuse of our right triangle, and the y component is the vertical side here. So if we look at where our angle is, we can see that the force of our pull in the y direction is opposite of that, not adjacent. So that means we're going to be using sines. So we can write that the force of our pull in the y direction is equal to the force of our pull times sine of 30. And if we plug that into our handy dandy calculator, we know that this is 75 newtons, that was given, times sine of 30. And so this ends up being 37.5 newtons. Okay, well, what about the force of gravity? Well, the force of gravity is just equal to our mass times our acceleration of gravity, g. Our mass of our little box is 10 kilograms. The acceleration of gravity is 9.81 meters per second squared. We're going to pretend that that was a pretty unit. There we go. So then 10 times 9.81 is simply 98.1 newtons, or kilogram meters per second squared. Newtons is the same as that unit. All right, so now we have both of these, so we can combine them into our little equation here and solve for our normal force. Okay, so we know our normal force is equal to our, the normal force plus the force of our pull in the y direction, so plus 37.5, minus our force of gravity, so minus 98.1, is equal to 0. I'm just going to add this over and subtract this. We end up solving that our normal force is equal to 60.6 newtons. There we go. That was a lot of work to get to this one force, but we did it. So now we can plug this into our little friction equation up here. So we know that our force of friction is equal to our coefficient of kinetic friction, or 0.35, times our normal force, which is 60.6 newtons. So then the force of our friction is just going to be equal to 21.21 newtons. And we are done. That is the force of our friction. And just as a note, to note the direction, it is pulling backwards here. Okay, but now we are almost out of room on the board, so I'm going to erase all of this. Feel free to take a screenshot if you need it. Let us move on, though, to the next part of our question. Now that we have solved for force, for the force of friction. Okay, well, what about the work done to the force of my pull? So the work done by the force of my pull Well, we know that the work done by any force is equal to the parallel component of that force to the object's motion times its displacement. So the parallel component of the force of my pull here, well, the direction of my motion here is horizontal. So the horizontal component of the force of my pull is what we're looking for, just like this. So the force of my pull in the x direction. And we know how to calculate that. That would just be, hey, well, to calculate the y component, we had to use sine. So we know to do the x component here is just going to be cosine. So the parallel component of the force of my pull is just going to be equal to cosine of 30 times the force of my pull, or times 75. And we know that that is going to be equal to a number that I don't have written down. Okay, but we know that when we multiply that by displacement, that's what gives us the work done by the force of our pull. Goodness gracious, words are so hard today. Words are really hard every day. But okay, so the work done by the force of our pull is going to be equal to the parallel component of our force, which is the x component, times our displacement in that direction. So we know our force is cosine of 30 times 75 newtons times our delta x, which is just 6 meters. And that is a positive 6 meters because it's to the right, and our force is also pulling to the right, so this is a positive force. Both of those are in the same direction, and we end up getting a positive 390 joules. Alrighty, and there we are. We are over halfway done. Okay, so those were the first two things we needed to calculate. Now, let's calculate the work done by our friction. Oh, a quick note. This is a positive value for our work, which makes sense. As we pull our object, it makes sense that we should be giving it energy, right? As if we're causing it to move. We're pulling in the same direction that our movement is pointing. So we have a positive value for work. Okay, now let's talk about the work accomplished by friction. So we know that the work accomplished by friction is going to be equal to the parallel component of friction times our displacement. So our parallel component of friction, well, this is, well, all of our friction. Our friction is exactly horizontal, and our motion is exactly in the horizontal direction. So this is going to just be our force of friction, which we already calculated for, but it's pulling in the negative x direction, right? So this is going to be the negative of this. So this is negative 21.21 newtons. That's negative. Times our delta x, our displacement, which is 6 meters. So whenever we multiply that out, this is going to give us negative 127 joules. Work due to friction is negative 127 joules. There we go. And again, this makes sense. We have a negative value for work, which means that friction is taking energy out of our system. It's taking energy away from the box. Well, friction is what's causing the box to slow down, right? As it goes slower, it feels like that should mean a lower energy, and that's exactly what's happening here. So that's what this negative value means. That's what we would have expected, as our force of friction is pointing in the opposite direction of our displacement. So everything's good there. Now we just have to calculate our total work, and that's not that bad. That is just like the sum of our forces is equal to, well, all of our forces added together. That's all we're going to have to do here. So our total work is just going to be equal to the work due to the force of our pull and the work due to friction. So the work due to the force of my pull and the work due to friction. And now you might be saying, wait, but Beth, I have more forces than just these two acting on my box. Why don't we have to calculate the work done by gravity or the work done by my normal force here? And those are great questions, and the answer is, we technically kind of do, but the answer we're going to be getting is 0. Because these forces are perpendicular to the direction of our motion, which means they do no work. So you can think of me as having like an invisible work due to my normal force and work due to the force of gravity here, but they're just equal to 0 because they are perpendicular to our displacement. So if we went through and we did want to calculate out, for example, the work done by gravity, well, we're going to be talking about the parallel component of the force of gravity. Gravity is pointing exactly straight down. The horizontal component of gravity is 0. So we're just going to be ending up with 0 for both of those values, which is why they aren't present here. But they kind of technically are, just invisibly. Okay, so we calculate our total work just by summing up our non-zero works. So this is equal to the work of the force of my pull, which is 390 joules, minus the work that friction did, which was negative 127 joules. So if we sum those up, we get a total work of 263 joules. So that is our total work, which is positive. So overall, on the whole, energy is being put into our system, being given to our box, but not as much as would have been in the absence of friction. This is taking away energy a little bit. All right, but that was a lot, but we did it. That is the force of our friction, the work done by friction, the work that I did on this box of books by pulling it, and the total work that is happening on our box. Thank you so much for sticking with me through all of that. If you are enjoying these videos, if you're finding them helpful at all, please just leave us a little comment. I promise you we read all of them and they make our day, whatever you do. And hit a little subscribe if you really want to keep up with us as we keep making these. But outside of that, thank you so much for sticking with me through all of this, and happy physicsing.